Hello everyone, this is the introduction for lab number 4 using op-amps to create integrator and differentiators. So let's first focus on the integrator, and there's going to be something called practical integrator. So we start from this inverting amplifier. Your input is connected to the negative input as shown here, and if you replace this feedback resistor into a feedback capacitor, then it turns into a ideal integrator. So previously in the inverting amplifier, your output was RF over RS negative times your VN, and in your integrator it's going to be 1 over negative, because still this is based on an inverting amplifier. Your input is feeding into the negative input. There's a negative sign there, 1 over RSCF times the integration of your input. So the important thing is, by adding this capacitor, the waveform shape that you see from the output voltage should be changing. So for example, in this inverting amplifier, you had an input that was a square wave, and your output is going to be a square wave, but the amplitude changes and it flips over. So you see it flips over, but still that's in the same shape. But for this integrator, we expect that we would like to have an output that is integral of your input. So we expect to have a different waveform shape coming out, right? So that's what we expect, and in case we see something different from here, that's going to be kind of error from your circuit. So the frequency response, the output over input gain in dB scale, and if we plot that into a log of frequency, then we're going to have like a straight line going down this. On the other hand, the problem here is at low frequency in this regime, then this ratio becomes very, very large, which close to infinite, which is not possible because there's almost no way to create infinite gain. So people came up with a advanced concept that is so-called practical integrator. This practical integrator is that on top of this RSCF, we are adding a resistor, RF, and this resistor is assumed to be much greater than this series resistor. Okay, so by adding this resistor, we are chopping down the frequency response. That was the problem in the low frequency range, and it's going to follow the ideal line like this in the high frequency range. Okay, so this was kind of the problem in the low frequency, so you are chopping that down like this, and then it starts to follow the ideal curve. And so this is pretty similar to what we've seen from the RC circuit, right? We can identify there's going to be a cutoff frequency that starts to bend, and for this one, an interesting point is there is a frequency that is called 0 dB frequency, which is covered from the lecture, and this cutoff frequency, and this is 0 dB frequency, okay, and this is defined as 1 over RF CF over 2 pi hertz, and this is 1 over 2 pi RS CF hertz. Okay, so what we can see from here is that we would like to use frequency that follows the ideal line. Again, like I said before, we are expecting to have a different shape, okay? And that is realized by this straight line. Because in the ideal world, if you had this kind of straight line, your response is going to be an integrated signal. However, in practical situation, the curve is going to change like this. So this regime is not going to give you integrated, and this yellow highlighted regime that follows the ideal line is the range that we want to use for integrator, right? And to be more specific, we would like to use somewhere between here and there, because below 0 dB frequency, your output is going to be very, very small. And although it is being integrated, we don't want to get like a very small signal. So we would like to have a signal that has reasonable output amplitude, and it is slightly above this cutoff frequency, so that you see around this cutoff frequency, it is being kind of bent down. So it is not ideally following this straight line, but if you move up, maybe it really depends on the applications, but if you slightly move up the frequency, it is going to follow this straight line much more closely. So you would like to use the frequency range between somewhere slightly above the omega c and below the omega 0. Okay, so this is the integrator, and in the lab we are going to form this ideal integrator and the practical integrator. And for the ideal integrator, you're gonna measure your frequency at this point, and for the practical integrator, you are going to measure your output and input voltages at low frequency, somewhere mid frequency, and somewhere like high frequency. Okay, and this is about 10% of your omega c. This is slightly above, say 1.2 of your omega c, and this one 5 to 10 times of your omega c. Okay, next up is the differentiator. Okay, ideal differentiator, and we have the practical one. So let's start from the integrator circuit. So like I said, it is has the same topology as the inverting amplifier, but this guy is changed to a capacitor. But as you know very much, integrator and differentiator, it's like you flip flip the sign, and you are going to get the integrator. So if we change this capacitor here, and this guy goes there, then it is going to be integrator. No, a differentiator, I'm sorry. So from here, you'll see your input signal is being integrated, and your integrated signal, if that goes as your input, you're going to see differentiated output. Okay, and again, we expect a different shape between your input and the output. For these inverting amplifier, non-inverting amplifier, they are simply amplifying the signal, so we expect that the shape is being the same. Okay, square gives a square, sine gives like something like a sine. But in these integrator and differentiator, we would like to change the shape. And the square wave is going to be like a sawtooth, and sawtooth, if you differentiate it, it's going to look like a square wave. And if we draw the frequency response, again, this guy in dB scale, and this is log frequency, different from the integrator, a straight line going down. In this case, straight line going up, and what is going to be the problem? This part is going to be the problem, because you know your output over input ratio, or the gain, is going very, very large, which is not possible. So you are adding a additional series resistor, and that is chopping down your frequency response. So it's solving the problem you had in the high frequency regime. And similarly, we're going to have a cutoff frequency and a 0 dB frequency. Okay, and this is going to be defined as 1 over 2 pi RS CS hertz. This is going to be defined as 1 over 2 pi RF CS hertz. So which area do you want to use for the differentiation? We would like to use the frequency range starting from here down there. We don't want to use the frequency range here. Again, the response of your practical differentiator is different from the ideal one. The ideal one, it always gives you the output that is a differentiated signal, but you see the practical one is different from your ideal. So this part is not going to give you your expected signal that is differentiated. Okay, but if you're exciting at the frequency that is lower than this cutoff, then you're going to get a differentiated signal, since your practical differentiator follows this ideal line. Okay, and to be more specific, we would like to use the frequency range starting from here up to there. This is the range that you would like to use, because if you go below this omega 0, then your output level is going to be very small compared to your input. So why we use that? We would like to have a decently amplified signal as your output. Okay, so in the lab, again, you're going to form this circuit and that circuit, and for this ideal differentiator, you are going to excite your signal at this is omega mid. And for the practical one, you would like to see whether the low frequency, mid frequency, and the high frequency, how your output is going to be different. So your mid frequency is going to be slightly smaller, lower than your omega c. So maybe it's going to be 0.7, 0.8 of your point times of your omega c. This is going to be 5 to 10 times of your omega c, and this is going to be about 0.1 of your omega c. Okay, so this is your low, mid, and this is your high. Got that? So we kind of expect that if you're exciting at this mid, so it is following this straight line, and if you're exciting at this low frequency, it's followed the straight line. So these two are giving the differentiated signal, while if you're low frequency input, this guy is going to give you a signal that is differentiated, but the output is going to be very small. And the frequency above this cutoff frequency, which is your high frequency, it's going to give you a response here, which is not following the ideal curve. So we expect that the response at this frequency regime is not going to be differentiated. Not differentiated. Okay, so for this lab, again, it's going to be a pretty busy one, and I strongly recommend bring your lecture notes so that you can have these numbers to select at the frequency that you are going to use. And there's going to be a check sheet on Folio. It's going to help you to make sure you get all the data before you leave the lab. So make sure you bring this check sheet from Folio, and we're going to build like 4 circuits: integrator, practical integrator, differentiator, practical differentiator. And for those, we are going to have 3 frequencies: the low frequency, mid frequency, and high frequency. Low and mid are simple. It's about like 10% of your cutoff frequency. It's going to be 5 to 10 times of your cutoff frequency for the high frequency. But for the mid frequency, you want to keep slightly above your cutoff for the integrator and slightly below of your cutoff for the differentiator. So make sure these frequencies are selected correctly. And in the lab manual, it says use like 50 hertz for your mid frequency, but I don't recommend doing like that, because this is going to depend on the FC that you select, and this FC is dependent on your R and C values. So you're going to have different R and C values each group, and it's not going to meet the condition of 50 hertz all the time. Okay, so you, for example, again, for an integrator, you would like to use a frequency about here for your mid, that is slightly above maybe 1.2, 1.3 times of your omega C, and high frequency, and this is going to be your low frequency. Okay, and again, for the low frequency, your response is different from the ideal case, so you're going to expect that your output is not being clearly integrated. But for this frequency and for the high frequency, the curve kind of follows the ideal case. So you expect that your signal is integrated correctly. Okay, and finally, this is from the last lab, and we need to connect supply voltage to the op-amp so that it is activated. And let me check this thing one more time. So here we have 2 batteries. Again, this is one battery. This, you see, this is plus and this is minus, this is plus and this is minus. And by having this selected as a series condition, you're going to have the battery like this and the battery like that. These 2 are being interconnected like this. Okay, and this corresponds to here, this negative corresponds to this one, this positive corresponds to here, this negative corresponds to there. Okay, and you see these 2 are connected internally, so these 2 terminals are connected internally. So you can either use here or there as your reference or the ground, because we are going to use this center as a ground or reference. And with respect to this point, this is going to be positive 15 volt, and with respect to here, this is going to be negative 15. Again, we don't have any negative voltages from the batteries, right? We just make it relatively negative. Okay, so that's important. It's very important that we select this ground or the reference for all your circuit. So either here or there are going to be your ground, and this is going to be your positive supply voltage, and this is going to be your negative supply voltage. So do not use these grounds. These are not supposed to be used for our purpose. Okay, so let's make sure that we know how to activate those op-amp circuits. So this is it for today. So bring the lecture note, check sheet, and correctly select your low frequency, mid frequency, and high frequency for the corresponding integrator and differentiator. Okay, so this is going to be another busy lab, so let's make sure we can get all the data before we leave the door. Thank you.